Welcome back to the last lecture on chemical bonding, and we're going to be looking at electronegativity, which in your textbook is page 36 to 42. So when we're looking at chemical bonds, bonds occur between atoms because the positively charged protons of one atom are attracted to the negatively charged electrons of another atom. So it's because of electrostatic force. So it's an attraction between two separate atoms. For ionic bonding, the loss or gain of electrons in order to fill an energy level, it happens when there's a big difference in electrostatic force. So it happens when one atom isn't really all that attracted to some of its electrons, and another atom comes by and is really attracted to its electrons. And we'll show you what that sort of looks like. Covalent bonds happens when there's little difference in electrostatic force, or it happens when both of those atoms are attracted to their own electrons the same amount, with the same magnitude. And this is called electronegativity. Electronegativity is an atom's ability to attract electrons. It's on a scale between 0 and 4, and atoms with higher electronegativity are strongly attracted to the valence electrons of another atom. And you can find the electronegativity atom. It's on your periodic table. And it's underneath the atomic number. And the type of bonding actually occurs along a spectrum. So here's the here's your periodic table, or the elements on your periodic table. Your periods are shown down here on the graph. There we go. Here's our periods. So periods 1, 2, 3, 4, 5. This right here would be the electronegativity of hydrogen. Over here are the noble gases. Notice that they have no electronegativity because they're never attracted to anybody else's electrons. So over here, where you can't see it, this would be where helium is, down here. Right here we have lithium, beryllium, and then we jump across to boron. If I can find my pen tip here. Looks like boron's in group 13. So here's boron, carbon, nitrogen, oxygen, fluorine, which has the highest electronegativity, and then the noble gases, again, you can't see their electronegativities because they're 0, so neon would be right up here underneath the hydrogen before the fluorine. And what you should notice is that as you go across each period, so as you go across a period, electronegativities increase. As you go through a period. When you're as you go through a period. When you look at groups, and we'll just look at the group 1s here, the atom with the lowest electronegativity in group 1 is at the bottom. It's francium. And as you go up towards the top of the periodic table, electronegativities increase. And if you look at each group, the alkaline earth metals are here again. You notice that our electronegativity, the size of these bars, increase as you go up, or as you go towards the top of the periodic table. The value of electronegativity is increasing. So electronegativity increases by group number. It also increases by period. So electronegativity is always increasing this way. So, and it's affected by two things. It's affected by the size of the nucleus and the distance that nucleus is from the valence electrons. So, and here's just a smaller one. It's just the main group elements. We should see the same thing. Electronegativity increases as we go towards the top of the periodic table, and electronegativity increases as we go through each period. So in any group, the electronegativity increases from bottom to top. And so this should show us that francium on the bottom left of our periodic table has the lowest electronegativity, while fluorine has the highest. It means francium isn't really all that attracted to its valence electrons, whereas fluorine is very attracted to its valence electrons. Now, one of the reasons this happens is as we go through our periodic table, here's a periodic table showing you the relative size of each atom. So, for example, hydrogen is the smallest atom on the periodic table because it only has one proton and one electron, and most of its size is determined by protons. As you get to closer to the bottom of your periodic table, and you can see that the transition metals, there's something weird going on. They seem to get smaller and then they seem to get bigger. So there's more to it than what we're talking about now. But what we generally see is that as you go through a group, the size of the atom gets smaller and smaller as you move forward through the group, except for the noble gases. So the size decreases as you go through a period. And the reason this is happening is because, remember, lithium, 2 energy levels for electrons for period 2. Lithium only has 3 protons, so a small positive charge. Fluorine, on the other hand, has 9 protons. They have the same number of energy levels, both only have 2 energy levels, but there's a much bigger positive charge in the center of a fluorine atom. And this trend holds true through each period. Same thing here. These all have 3 energy levels. But as we go up, the charge, the magnitude of the nucleus increases. And that's what causes the size to shrink. And as these atoms shrink, they're going to have higher electronegativity. Since they're smaller, they can get closer to other atoms. The smaller you are, the closer your positive center can get to other atoms. And so there's 2 kind of competing trends. The attractive forces between 2 atoms decreases as the distance between their centers increase, which makes sense. The farther away that positive nucleus is to the valence electrons of another atom, the less electronegativity is going to happen. Attractive forces also increase as the magnitude of the charges increase. So if we take a look at something like barium and fluorine, as they would be attracted to a carbon atom. If we take a look at barium, and we take a look at its size, now its molar mass, or its atomic number, is 137. This means it has 137 particles in its nucleus. It's also in group, or I should say in period, 6. Which means it has 6 energy levels. So that means it's a big atom. So barium would look something like this. And remember, all of its positive charges are right in the center. So right there is the nucleus of barium. That's where its positive charge is. It's a big positive charge, but again, it's far away from the outside of the atom. When we look at fluorine, fluorine only has 9 particles, or I should say 19 particles. Its molar number is 19. So it has 19 particles in the nucleus, but it only has 2 energy levels. because it's in group 2. So fluorine is, by comparison, much, much smaller. And there's its positive charge right there. When we look at carbon, carbon's even a little bit smaller than fluorine, or it has less charge. So carbon would be a molecule, say, about this size. Now fluorine is going to be bonded very strongly to carbon's valence electrons. Its positive charge can get much closer than barium. So a barium carbon would be a very big barium, and here's our carbon, and this distance between its nucleus and carbon's valence electrons is fairly big. When we look at fluorine, fluorine's very small, even compared to carbon it's small, and so the distance between its nucleus and valence electrons is much smaller. So therefore it's going to have a much higher electronegativity. Because of its small size, its charge, its positive nucleus can get much closer to the valence electrons of another atom. So, it turns out that we can predict the bond type, whether it's a molecular bond, covalent bond, based on the difference in electronegativity between two atoms. So when we have two atoms with very different electronegativities, electrons aren't going to be shared, they're going to be transferred. If one atom has a really strong pull on electrons, on valence electrons, and the other one doesn't, then those electrons will be stripped from the one that doesn't. And this is going to be an ionic bond, and these happen when the electronegativity is greater than 1.7. If the electronegativities are slightly different, but not all that much different, the electrons are going to be shared, but they're not going to be shared equally. One of those atoms is going to be pulling harder on those valence electrons than the other one. This happens when the electronegativity is between about 0.5 and 1.7, and then it's going to be something called a polar bond, or a covalent polar bond. And we can mark the bond ends with these little delta symbols. And I'll show you some examples of those soon. If the difference in electronegativity is less than 0.5, then the electrons are being shared almost equally in terms of charge. One might be slightly more than the other. For us, they're slightly polar covalent. If it's 0, if the difference in, delta means difference, that's a little triangle, if the difference in the electronegativity is 0, then we have a non-polar bond. And so here we're going to look at hydrobromic acid. When we do the math, we find the electronegativity of hydrogen, the electronegativity of bromine, and we subtract the two, and we take the absolute value. These vertical lines mean absolute value, and the absolute value is 0.8. Since 0.8 is between 0.5 and 1.7, the bond is called polar covalent. And when we draw it, we show that it's a polar covalent bond. There's two ways to do it. You can use delta notation. Bromine has a higher electronegativity. Its electronegativity is 3, which means it's pulling on this pair of electrons harder. So these electrons are being pulled towards bromine more than they are being pulled towards hydrogen, which means bromine is going to have a slightly negative charge around it. It has slightly more electrons, or the electron, than it does protons, because it has this extra electron close to it. Hydrogen, on the other hand, is having electrons pulled away from it, so it has a positive charge in its nucleus. Its negative charge is being pulled away from it, or it's farther away, so it's going to have a slightly positive charge on the hydrogen end of this molecule. We can represent it with delta notation, or we can represent it with a dipole arrow, in which case this little plus here is kind of like the plus sign over the positive one, and the arrow is showing which atom is pulling on the electron. So we put a plus over the positive atom, the one that's losing the electron, or that it's kind of losing the tug of war, if you like, and an arrow pointing to the one that's winning it. So here's our bonding continuum, and it is a continuum. Bonds that are between 0.7 and 1.5 and a bond that is at 0.7 is going to be less polar than a bond that has a difference in electronegativity of 1.5. If and the same holds true for any of the numbers. So a bond with an electronegativity of 1.8 is going to be less ionic than a bond with an electronegativity difference of 2.8. The bigger the difference, the more ionic it is. A bond with electronegativity of 0.4 is going to be slightly polar, while a bond with a difference in electronegativity of 0 is not going to be polar at all. The electrons are going to be shared perfectly equally between those two atoms. And so sometimes you'll see these charts where they talk about the nature of a bond, and you don't have to memorize these percentages by any stretch of the means, but what you should see is that as you start getting past that difference in electronegativity of that 1.7-ish area, you get mostly ionic bonds with high electronegativities. You get these polar bonds that have some ionic properties in this kind of middle zone. You'll see that there's some ionic properties and some covalent properties. And then as you get below that, or around that 0.5 region, these are really nonpolar, polar, covalent, and these are really the ones you're going to be calling ionic. The ones that are kind of close down by this 1.67, it depends on the chemicals or the atoms. Sometimes they're called ionic, sometimes they're called polar covalent, but it depends on what we're working with. So we're going to determine the nature of the bond between nitrogen and hydrogen. So, and all this is, it's simple math as long as you remember to do it. So we're going to find the difference in electronegativity between nitrogen and hydrogen. And to do that, we just find their electronegativities and subtract. So the difference, nitrogen is 3.0, hydrogen is 2.2. So we get a difference of 0.8. Since it's greater than 0.7, so greater than 0.7, this is going to be polar covalent bond. And to represent it as such, we would go N, H, and the arrow would go this way. Oxygen and iodine. So the difference in electronegativity between oxygen and iodine is equal to, the electronegativity of oxygen is 3.4 minus 2.7, and we get a difference of 0.7. So, since it has a difference of about 0.7, this bond is going to be polar covalent. And if we were to draw it, since oxygen is more electronegative, and it doesn't matter the order, if we go like this, and we can say this end is slightly positive, this end is slightly negative. The other way to represent it is that way. Between two chlorine atoms. So, notice that we're just talking about specific bonds. We are not talking about molecules yet. So, both are chlorine, both are 3.2. So this is going to be nonpolar covalent. And we can't represent any bond dipoles. I guess the best you could do is you could say it looks something like, the bond looks something like that. There's no dipole, so there's no markings above the atoms. We can also list bonds in order of decreasing polarity. And this time we don't even have to classify the molecules, we're just going to calculate differences in electronegativity. The first one is lithium and phosphorus. Lithium has an electronegativity of 1. Phosphorus has an electronegativity of 2.2. Again, I'm just grabbing these off the periodic table. So 1.2 is the difference for that one. Delta EN for carbon and fluorine is equal to, carbon is 2.6 minus fluorine is 4.0. And so the difference is going to be 1.4. And we have carbon and oxygen. So delta EN between carbon and oxygen is equal to 2.6 minus 3.4. And here we get a difference of 0.8. So there's our three differences in electronegativity. And we want to order them by decreasing polarities, so the most polar first. So it would be the C. F is the most polar. LIP is the next most polar. And the least polar would be CO. All of these bonds are polar covalent bonds. But the carbon-fluorine one is the strongest of the group. We can also classify bonds as being polar and nonpolar, and we can talk about them being as, and we can indicate for polar bonds what their polarity is. So for chlorine and phosphorus, it's equal to chlorine is 3.2, phosphorus is 2.2, and we get 1.0. It's between 0.5 and 1.7, so it's polar covalent. And so to represent the polarity, we can put a phosphorus, a chlorine. Chlorine's more electronegative, so we'll go like that. For potassium and iodine, potassium is K, iodine, the electronegativity of potassium is 0.8 minus iodine is 2.7. So we have a difference of, I believe, 1.9. This is greater than 1.7, so this would be an ionic bond. And you wouldn't really indicate it using a polarity arrow because this is now almost a full charge difference. So potassium will be positively charged, and iodine would have its full valence energy level and be negatively charged. It would be iodide. So when representing what the polarity is, this is for only polar covalent bonds. This we would use for mostly ionic bonds. So we use a continuum because some bonds behave as ionic bonds under some conditions and covalent bonds under other conditions. An example would be for hydrochloric acid. If we take a look at this acid, its difference in electronegativity between hydrogen and chlorine is, we've got 2.2 minus 3.2, so it's 1.0, which means it should be polar covalent. And when it's in its pure form, it acts as a polar compound. It acts as a covalent bond. It's an individual molecule. It's a gas. It floats around in the air, so it acts like a molecular compound. When you dissolve it in water, however, it actually ionizes. It forms H+ ions and chloride ions. So hydrogen ions and chloride ions, it dissociates, and so now it's behaving more as an ionic molecule or an ionic compound. So its bond, since it's a little bit of each, this continuum shows us that as you move through the continuum, atoms can have different characteristics depending on their differences in electronegativity. So that's the end of Chapter 1. There are some more practice problems that cover Chapter 1, questions 1 to 13 in Appendix B, near the back of your book on page 750. The solutions are on page 741. And once you're done those and check the answers, it'd be a good idea to try Assignment 1. Get your mark for this before you try the chapter test. So Assignment 1, get it marked. If you have questions, contact me, and then try the chapter test.